everyone, my name is Barkat. Welcome to my video project about the role of mathematics as a language, where I will use components like logic and Basque numbers to show that mathematics can be applied as a language to get distinct behaviorisms. Before we dive into the concept of how mathematics plays a role as a language, let us first understand. What is mathematics? What is mathematics? Is it defined as the study of numbers or the science of numerals? As stated precisely by the Greeks in 500 AD, it is known as the collection of techniques for measuring, counting, and accounting. Or, it's interpreted as the study of number, shape, motion, and change, and space. These connotations represent mathematics in a generalized sense of understanding. But, what if mathematics was illustrated as a language? What if language was formed through a series of patterns and behaviorisms? To understand this, let's see how we can compare the fundamental units of mathematics with English. We can see that just like the English nouns, which are the basic fundamentals of English, which represent animal, place, name, and thing, the fundamental units of mathematics start with counting numbers, decimal values, and fractions. They make up the root of mathematics, from where it is built upwards. Next, just like the verbs connect nouns with action words, the math operators connect values. We also know that for every action there's an output generated, which is the relation in the English language. In mathematics, relations are represented as equalities and inequalities like these. When one wants to change the meaning of a sentence or change the structure of a sentence, then one uses punctuations and conjunctions. The ability to change the way things are portrayed are also present in mathematics. The brackets play this role. Some examples are brackets over PEDMAS techniques and others representing a function. Lastly, nouns and objects can be represented by placeholders in the English language. These are known as pronouns. These pronouns temporarily hold values and can be replaced by multiple nouns. These placeholders in mathematics are referred to as variables. These variables hold temporary values and can be replaced by a group of certain type of values or just one specific value. Here x and y are placeholders. After understanding these fundamental units, we can explore the concept based of logic and reasoning called semantics, which is a certain type of behaviorism and pattern. The combination of mathematics in terms of logical symbolisms and representations will help us understand how mathematics acts like a language. Now, these operators are known as logical connectors or logical operators. These elements include and, or, if, then, if and only if, not, etc., and have a specific representation and role. The AND operator returns true only if both the antecedent and the consequent value, which is the first unit and the second unit, are true. The OR operator returns true when either one of the units is true. The implication is used for if and then statements, where the antecedent can only occur if the consequent occurs. The double implication holds for both, and this last one is the negated value, which is representing untrue values of the negated value. Now, these act like mathematical operators and can be represented with the letters P and Q. When combined, these expressions can have the ability to form a sentence in the English language, which can be translated into properties like proof structures in mathematics. Now, let us understand an example where these symbols and properties are being used. If you're a student, then you are smart or motivated. If you observe, there's an implication format seen here. If the girl represented is a student, only then she is smart or motivated. So we use if-then operator, which is the main operator, and put the OR operator between study and motivated. And then put P and Q and R as what they represent and put it all together. We then get the symbolization of the example. These kind of sentences also have conclusions. Just like different proof structures in mathematics, we can also use proof structures to form conclusions in a derivation, which I will show you after. I'm sure you're familiar with proof structures like direct derivation, contradiction, contrapositive, but these two, universal and conditional, are different. A universal proof structure is used by removing the for all representation in the statement and proves the generic form. For example, all apples are green can be represented by one generic apple is green, where you show a for all line and then remove the for all to show the generic line. Similarly, the conditional proof is one where you will see a false value and you can denote a contradiction by taking the negation of the consequent. This proves the whole proof structure of for all x, px implies gx. All apples are green. Now, let us look at the truth table for a similar premise and find a conclusion using a previously mentioned proof structure. Through this proof structure, that is proof by contradiction, it is easier to understand the statement's relation and conclusion in terms of representing it mathematically. You will see that in this truth value, after getting its last values, we see a contradiction, that is an F or a false value. This explains how language plays an important role in mathematics to draw conclusions. Now, unlike the truth table pattern, there are predicate logic rules, which are inbuilt and help us derive and achieve a relation. To understand this, we need to understand rules. Okay, let's get into it. The first rule. The simplification rule simplifies an expression to give just one of the predicates. The MTP or the modus tollendipotens rule takes two forms and returns the negated value of the expression. The MT takes a conditional form and a negated value and returns the negated antecedent. The MP takes a conditional form and the consequent value and returns the antecedent. The CB takes a biconditional and returns one part as a conditional. ADD, as it sounds, adds two elements by the OR operator, whereas ADJ adds two elements using the AND operator. The QN takes the negation of the existential or universal and returns its opposite. The existential initiation removes the singular scope and allows it to be represented in another variable. The EG adds the singular scope of the element and allows it to be represented as another variable. The universal initiation removes the for all scope. The DM, which is the De Morgan's law, takes the OR and returns the negated values. So just like this example, if negated value of P or Q is applied to DM, it goes to negated P and negated Q. The NC takes a negation of the conditional statement, returns it in an AND format. Okay. Now all these rules seem a little difficult to implement right now, but by the following proof that I will present, it will be easier to understand how and why these are used to form conclusions.
Prove that P and not Q implies not over the whole P implies Q. What we first do is show this conclusion. I'm proving this derivation in a software called Logic 2010. Now, in order to start and use all the rules that were told beforehand, we start with a proof structure. I notice that the proof structure is a conditional statement. So what I do is that I assume a conditional. This gives me the antecedent. I can now use the simplification rule for removing P and not Q separately. So line number 2, S rule, gives me P. Line number 2, S rule, also gives me not Q. Now, following the proof structure, I want to prove by contradiction. So either we find a P or a not Q's negated value and prove it using proof by contradiction, that is ID. Now, to do that, we first show the consequent. And we have to show that this is true So proof by contradiction assumes the opposite, which is assume the opposite, which is the unnegated value of P implies Q. Now, I can use line number 3 and line number 6 to give me Q. I did this using MP, modus ponens, which takes the antecedent and a conditional value and gives me the consequent. If I notice closely, line number 4 and line number 7 are negated values of each other. This can help me form a contradiction. Now, if I take line number 4 and repeat it, R for repeat the show line, then we get two lines under the same scope. If I say 7 number line and 8 number line are the opposites, ID, that are indirect, which stands for indirect, then the show line is cancelled. Why is this? This is because we were trying to prove something by using its negated value. So we created a contradiction. Hence, this whole line gets cancelled out because we proved it. To complete the proof, we have to follow the proof structure, which is the conditional proof structure that I started with by assuming the conditional. So I end the proof by saying, on number line, there is a conditional value. There you have it. The proof is now complete. And I hope you understood all the MP, ID, CD rules and that it is so easy to use. Okay.
Let's shift to the world of language with Basque numbers. Basque is a rare native language originating from Spain and France and is difficult to understand and pronounce. But with the help of mathematics, interpreting and finding patterns in them makes it easier to understand and comprehend. I will explain the concept of Basque numbers with a simple linguistic problem that was mentioned in the International Linguistic Olympiad. So let's dive right into it. We have the following problem at hand. I know, the first thing that goes on your mind is how are we ever going to understand this? But wait and watch. Mathematics does wonders. Our main goal is to find and fill the blank by translating all the lines. Let's understand the basic level of mathematics. We can interpret that a combination of two single elements is likely to be a two-digit number. Elements like Hogita Hamar, Hogita Bost, Hogita Hama are these kind of two-digit numbers which can be of a relation of addition or multiplication between them. In these examples, they have a common element Hoge, which is a multiple of the base number. Now, Hoge can either be 10, 20, or 30 base. So, we take Bai times Bai equals Lau as 2 times 2, where Bai, Lau, Bost, Hamar, Hiru, Bidratsi, and Zazaspi are single elements. Now, while if we take pi times pi equals Lau, that's an educated guess, only because if we take any other number, it will be a huge number for line number 10, which is not what we want. So we take 2 times 2 equals 4, where pi is 2 and Lau is 4. Next, we plug in the values that we know for sure. We see that if we take Hoge equals 10 and we put it in equation number 3, we get 2 times 5. But to confirm it in number 2, we don't get the value 5. Value 10. So we cannot say that Hoge is 10. Instead, if we take Hoge as 20, then this calculation is possible. So Post is equal to 5, Hama is equal to 10, and Hoge is equal to 20, according to our educated guess. Next, we know that on line 4, Hama plus Bost is 10 plus 5. Thus, Hiru results in 3. Additionally, confirming the result 3 on line number 5 is 3 times 10, which is 30. On line number 6, we have 5 times 5, which is 25, with the values that we have already inputted and found. And so Hogita Boost is 20 plus 5, which is 25. Using Hoge taboos, we can draw conclusion that Hoge is 20, and we can also conclude this on line number 10 and plug in the value 20, which is equal to Hoge. Again, with these similar calculations, we can get Zazasp equals 7, Hogita Hama equals 35, Bedaratsi equals 9, Hirogita Hiru equals 63. And we notice that on utilizing the components and properties of mathematics, we can decipher a whole new language system and understand its basis of existence and grammar. We see that by the virtue of carrying out detailed study of patterns of predicate logic, we not only gained considerable amount of understanding of a former proof, but also realized that it was reliable means of establishing the mathematical truth. The study and explanation of patterns that are generated in terms of their relation to mathematics allowed us to decrypt patterns like the ones we did in Bass numbers. Through the understanding of mathematics as different components of language, we conclude that mathematics is a universal language and can be applied to get distinct behaviorisms using the components of logic and semantics and other various patterns. Thank you, and I hope you enjoyed my video and my insight in how mathematics can be used as a language in linguistics. Thank you.